So as I mentioned, we have only this one last bullet point left. This is chapter 6, compaction, and we have this one item, determine field unit weight. So this relates to basically compaction control. So how do you tell the in situ unit weight after compaction? So that's the topic for today. And for this compaction control, so determines field unit weight. As I mentioned, this is a way to control compaction effort. So you need a way to measure in situ unit weight to tell you if your end product meets your specification. Okay. And there are 3 standard methods for determining field unit weight: sand cone method, rubber balloon method, and nuclear method. And in this class, I'm going to focus on just the first one. And I have one example for sand cone method as well. And for the other 2, I have a little bit of background included in the slides. You can take a look at these slides, but I'll focus on the first one. And we'll have one example for sand cone method. For this sand cone method, this slide shows basically the device of sand cone method. We have this in our soil mechanics lab as well. In this device, there are a couple of components here. One is this jar here. It can be a glass or a plastic jar. And then you have this cone and metal plate. Okay. So to understand the sand balloon method and also the water balloon method, sand cone method, and also the water balloon method, they're actually pretty similar in principle. To understand this, so let me first draw this. So first you need to understand what we're trying to do when you're determining field unit weight, in situ unit weight. Okay. So let's say you have this compacted soil. Okay. And the way to measure in situ unit weight, at least for the first 2 methods, the nuclear method uses different basic technology. For sand cone and the water balloon method, what we're going to do, basically what you want is you take soil samples. So you dig a hole, okay, and you take soil out. So that's your soil sample. And use this soil sample to determine the unit weight. Okay. And when you think of unit weight, if you recall the definition of unit weight, so unit weight. And we have discussed the different types of unit weight. You have the total unit weight, moist unit weight, dry unit weight. But basically, you have the same format, weight over volume. Okay. If it's a dry unit weight, it's weight of solids over volume, over total volume. If it's a moist unit weight, it's a total weight over total volume. Okay. So that's the definition of unit weight. Then if you look at this process of taking soil sample from the field, so the easiest thing you can measure once you take those soils is to measure the mass and then calculate the weight. So this weight part, this is very easy to get. Weight, so this is easy to do. So take that much soil sample, you can always weigh it, and you can dry it to get the dry weight. So both moist and dry weight, these 2 weights are very easy to get. So you have weight of total weight and weight of solids. Okay. So this is total. And this is weight of solid. Weight of solids. So this is after oven dry. Okay. So these 2 weights are very easy to obtain. So you can always weigh your soil, get the total weight, the moist, and dry it to get the dry weight. And from these 2, you can calculate the moisture content. So you know how much moisture are in the soil. So you can calculate small w, this is moisture content. that's very, very easy. So everybody can do this. You can take a soil sample, wait, dry it, and wait again. So we get all these quantities. But what's tricky in determining the unit weight in situ is that volume part. So if you look at this definition, let me use a different color here. Okay, so this is the volume of that soil sample you took from the ground. So this is the volume, total volume. So when you take soil samples from the ground, unless you're using a shell pit tube, some fixture, the hole you dig on the ground is going to be irregular in shape. So this volume actually is the tricky part. So how do you know the volume of that irregular shaped hole you dig on the ground? So that's the tricky part. And that's where these first two methods come in. So sand cone method and water balloon method, they help you determine the volume of that hole by using materials with known densities. For the sand cone method, you use sand. For water balloon method, you use water to fill that hole. And for both materials, because you know the density of these two materials, as long as you know how much materials are used to fill the hole, you can back calculate the volume. Okay? So that's basically the fundamental principles of these two methods. We use materials with known densities, basically to figure out the volume of the hole. And for this sand cone method, so I'm going to explain this method in much more details. Again, water balloon method is basically sits on the same principle. So for sand balloon method, the material we use is Ottawa sand. So we know the density of Ottawa sand. It's right here. Okay. So in this method, this basically shows the procedure of the sand cone method. And so you have, so I've described the sand cone device. And then in the sand cone method test, if you look at this picture right here, so you have this jar with Ottawa sand. So we know the density. Okay, so we know the density of this material. And in the test, you basically, you dig a hole on the ground. So you dig this small hole. And then you fill the hole with Ottawa sand using this jar here. Okay. And then you calculate the dry unit weight. So how do we do this exactly? So I have one example here for the sand cone method. So basically for this device, so I'll explain this with an example. But on the right hand side, this is a picture of the sand cone device. Okay. So I'm going to use this example here to explain the sand cone method. Okay. So in this example, this is example 3. First, you're given compaction test results. Okay. So we have this standard Proctor test. You have compaction test results, moisture content versus dry unit weight. Okay. And then this slide shows the results from the sand cone method. So you conduct the sand cone test and you got the following data. Okay. So I'm going to explain all these data here. Okay. So first, this is the dry density of Ottawa sand. So that's the material I said you know the density. So you know the density of the Ottawa sand, 1560 or 1570 kilogram per meter cube. And then the cone, remember in the sand cone device, you have that cone. So you know the volume of that cone. And then you also know the density of the sand, so you can calculate how much Ottawa sand you need to fill that cone. So that's also given. So for a given device, you know the volume of the cone, you know the density of the sand, you can calculate this mass here. Okay, so that's also given. And what you measure during the test is the mass of jar, cone, and sand before you conduct the test. So that's basically the total mass. And then after you fill the hole with Ottawa sand, you measure the mass of jar, cone, and sand again. So that's after use. Okay. Right. So with this, you can actually calculate. I'm going to first calculate this mass here. So this is a mass of sand to fill the hole on the ground. So this is. So with the first few numbers, I can first calculate how much sand we need to fill the hole on the ground. So this is going to be 7.59 minus 4.78 minus 0.545. The result is 2.265 kilogram. Let me explain all these numbers here. The first one is 7.59. So this is basically the total mass before use. So that's this number here. Okay. And then that second number, 4.78, this is the total mass after use. So that's this 4.78 number here. The difference between these two are basically the sand in the cone and the sand in the hole. So that's the difference. So to get the sand in the hole, we need to subtract the difference by this last number, which is the sand to fill the cone. Okay. So this is sand in the cone. So then the difference, final number, that's the sand to fill the hole. Okay. All right. So that gives you the mass of sand to fill the hole, and then you can calculate the volume of this hole on the ground. Okay. So we know the mass, we know the density of this Ottawa sand, then the volume of the hole is the mass of sand to fill the hole. So I'm just simply write this as mass to sand to fill over the density of this Ottawa sand. And density of Ottawa sand, as I mentioned, this is a material with known density. So 1570. Okay. So if you plug in that, so this is 2.265 divided by 15,670. Okay. So that gives you the volume of the hole. Okay. So this is going to be in cubic meter cube, 0.00014426 meter cube. Okay. So that's basically the volume of the hole you dig on the ground to take soil samples. So that's the sand cone method. And the rest of this example actually is basically, so once you figure out the volume, as I mentioned, you can then calculate the in situ unit weight, because you can always measure the weight of the soil. And now you know the volume, you can calculate the unit weight. Okay, so let's just finish this example here. So we know the moist to the soil. So this is in situ soil. This is not the Ottawa sand you used in the sand cone device. So this is soil from the hole. We know the mass of this moist soil. Okay, so this right here is 3.007. So we can calculate the density, moist density. Okay. So this is basically that moist soil is mass of the moist soil over volume of the soil, which is a basic volume of the hole. So again, you get the volume from the sand cone method. That's that. Then we substitute numbers here. That's going to be 3.07. So that's the moist mass of the soil divided by the volume, 0.00144426. And this is 2084. Unit is kilogram per meter cube. Okay, so that's density unit. So you have this basic moist density of soil. And then eventually our goal is to calculate the dry unit weight. Okay, so that's what the end product specification requires. So we need the dry unit weight. And to get unit weight, you can use density and then times gravitational acceleration to get unit weight. And there are actually two steps involved. So first, let's calculate the moist unit weight. Okay. So the moist unit weight is dry or moist density times gravitational acceleration. So if you plug in numbers, and I'm going to convert unit to kilonewton per meter cube. So it's 2084, that's moist density. And gravitational acceleration, 9.81, and they'll convert to kilonewton, so I'll divide that by 1000. So this gives us the unit weight in kilonewton per meter cube, 20.45 kilonewton meter cube. So again, this 1000 is to convert from Newton to kilonewton. So that's the moist unit weight. And finally, our goal is to get the dry unit weight. So this dry unit weight is simply moist over 1 plus moisture content. So gamma D, that's dry, is the moist unit weight divided by 1 plus moisture content. Okay. And moisture content, we know it's 10.2%, so that's given. Okay. So if you substitute numbers again, 20.45 divided 1 plus 10.2 over 100. So that gives you the dry unit weight in situ. So that's the dry unit weight of compaction in the field. This is 18.56. Again, this is dry unit weight in the field. So this part A of example 3 basically explain that sand cone method. So how you use the sand cone method to get eventually this in situ or this field dry unit weight. So that's gamma D field. So now let's just finish this example here. So once we have the measured this in situ dry unit weight or dry unit weight in the field, we can actually calculate the relative compaction. So relative compaction, so let's finish part 2 here. To calculate relative compaction, if you recall the definition of relative compaction, so this R here is defined as the unit weight in the field over the gamma D max from Proctor test. So this is gamma D max by 100%. Okay. So that's the definition. In gamma D max, I mentioned that's from your Proctor test. Can be either standard or modified Proctor test, depends on your requirement. So this is from that Proctor test. In gamma D field, that's what we just calculated from the sand cone method. That's from part A. So this is in situ dry unit weight. Okay. So again, in situ basically means in the field. And we have that from part A, and then the gamma D max, we need the Proctor test, the compaction curve. So that's what's shown on this right-hand side. So this figure on the right-hand side, that's a compaction curve. And you basically plot, let me go back here. So this is the standard or modified Proctor test results. You have moisture content, dry unit weight. So that's how you get this compaction curve. And the peak point of this compaction curve gives you that gamma D max. So this is basically gamma D max. And of course, you can get the corresponding moisture content. Remember, that's called optimum moisture content. Okay. For this example, we're not asked for that, but you can get that from the curve if you want. So this gamma D max is about 19. And now if you substitute this gamma D max into relative compaction definition, so R is basically 18.6 per A divided by 19 compaction curve times 100%. 97.7%. Okay, so that is the relative compaction for this example here. If not, so let me go back to our slides. Okay, so this is the Cengage method, and the rubber balloon method, as I mentioned, fundamentally it uses the same principle. So basically, you fill the hole with materials with known density, and for rubber balloon method, you fill the hole with water, okay? And you know the density of water, so you can back calculate the volume of the hole. And so that's why I say these two methods are very similar. And the third standard method is called the nuclear method. And this nuclear method uses a completely different principle. So this uses basically radioactive isotope sources, and it directly gives you the density, in situ density, the wet or moist density, and also the water content. Okay. So this is, we can say this is non-destructive, but you basically don't take soil samples, but you directly measure the moisture content and the wet density in situ. So that's the nuclear method. So this is the three standard methods to determine field unit weight. The next topic we have, I want to go over are these special compaction techniques. So far when we discuss field compaction, we talk about different types of rollers, some for clay soil, some for granular soil. And there are also some special compaction techniques. There are three included here: the vibroflotation, dynamic compaction, and blasting. So these are typically used for deep compaction of in-place soils. The vibroflotation, basically that is mostly for granular soils. So for the first two, actually, I included a couple of slides, and I also actually uploaded a couple of videos showing you the process of these special compaction techniques. For vibroflotation, if you focus on the picture on the left-hand side, so this basically shows the process of this compaction. So you basically lower this vibrofloat unit, and so there are two types of soils involved. So this is the in situ soil. Okay. So that's the soil you want to compact with this vibroflotation technique. And the second type of soil involved is this is called the backfill material. Okay. If you look at this picture, during this process, you're lowering this vibrofloat unit and use water jet, this high pressure water jet at the bottom to create a quick condition. So basically, you lower your vibrofloat unit to desired depths, and then you fill this hole with backfill material. So there are two types of soil, so in situ soil and backfill. Okay. So when you use this technique, the most important factors that may affect the result of this compaction are the grain size distribution of the in situ soil, and the second is the grain size distribution of the backfill material, so GSD. This slide shows basically the pattern, typical patterns of the vibroflotation probe settings and also grain size distributions, and specifically for backfill material. So you can quantify the suitability of the material for vibroflotation by this suitability number. And this is a function of grain size distribution parameters, so 1.7. So this is the suitability number, and basically the lower this SN number is, the more suitable the material is for use as a backfill. So for SN of 0 to 10, it's excellent for backfill. Okay. If SN is greater than 50, it's not suitable. So that's vibroflotation. And the next one is dynamic compaction. So for dynamic compaction, this is actually a pretty simple process. It's shown on this picture here. So what you do during this dynamic compaction is you lift a heavy weight, a heavy hammer to a certain height, and then just drop it. So that's dynamic compaction. And degree of compaction depends on these three factors: the weight of the hammer you use, the height of the hammer drop, and also the spacing of the location for the hammer drop. Okay. So that's dynamic compaction.